Oh, welcome and thank you for joining me in this lesson. In this video, we'll explore the graphs of reciprocal functions. Recall from grade 11 that we have studied the function y equals 1 over x, which is the reciprocal of the simplest linear function y equals x. Now, in grade 12, we'll extend this idea by studying the reciprocals of both linear and quadratic functions, and that will be the goal of today's lesson. Before we begin, let us review an important idea. When we add, subtract, or multiply two polynomial functions, the result is another polynomial function. And I want you to imagine having, let's say, for example, the function 2x plus 1 and the polynomial function 3x minus 4. So if you add these two, then we get another polynomial function of first degree. If we subtract them, it's the same idea. We get another polynomial function of the same degree. And if we multiply them, we get another polynomial function of second degree. However, if we divided these two functions, we won't get a polynomial function anymore, but we will get what we call a rational function. Now, unlike polynomial functions, rational functions will have a variable in the denominator. And when you look at the functions that we are looking at or analyzing today, a constant divided by a linear or a constant divided by a quadratic, the presence of a variable in the denominator presents the function the opportunity and the possibility of having the denominator be 0 at specific values of x. And this fact alone will give rational functions unique characteristics and distinguish them from polynomial functions. So as we work through the examples together, we will investigate the key properties of these functions and compare their graphs with the polynomials that we have studied so far. So let us begin with the reciprocal of a linear function. Recall that to determine the vertical asymptotes, we always inspect the restrictions of a rational function. And the restrictions are basically the x values that will give the denominator a value of 0. The equation of the vertical asymptotes, as a result, would be at x equals whatever the restricted value for the particular function is. So our x equals restrictions. When you think about it, what is the maximum number of x-intercepts or the zeros of a linear function? Well, a linear function of the form y equals ax plus b or mx plus b, as we're used to call it, is 1 and only 1. And we're going to say that the maximum number of restriction when this linear function becomes a denominator then will also be 1. And the maximum number of the vertical asymptotes, which are basically connected to the restrictions of the function, will be only 1 as well. So let's take a look now at the function f of x equals x and its reciprocal. And this is something that we have done in grade 11, but let's review this together one more time. So what you see here on the grid is the graph of the function f of x equals x. And what we are going to draw together is the graph of the function 1 divided by f of x. As you can see here, we are reciprocating f of x, or the y values of the points on the graph of the function f of x. So we'll begin here with this particular point. As you can see, the y value here is 1, which means that the reciprocal of 1, which is 1 over 1, will be also 1. So this point will also be a point on the graph of the reciprocal. Next, we have the value of y equals 2. The reciprocal of 2 will be 1 divided by 2. So for the same x value, we're going to have the y value here equal to 1/2 or 1 over 2. So next we have the y value equal to 3. The reciprocal of 3 will be 1/3. So this will be a point slightly lower than 1/2. Next we have y equals 4. And as you can see here, 1 over 4 will be the next point. So the quarter of a square here. And then we have 5 and 6 and 7. As you can see, the bigger the y values become, the smaller the reciprocals become. And when you think about it, as the values of y approach infinity, then the reciprocal of it will be 1 divided by infinity. And 1 divided by infinity will be a 0 plus, and will be a number, we say, very close to 0, above 0, but not equal to 0. So if we were to draw this section of the graph, by connecting all these dots, this is what we would see. It is very important to remember that in this case, the function or the graph of the reciprocal is not intersecting the x-axis, no matter how far we go in the domain. Now, the next important point is this one that I marked it in red. At this point, the value of the function is 0. When you reciprocate a value of 0, then we get an undefined number. And this is where the vertical asymptote of this function will be located, right at x equals 0. So why is this a vertical asymptote? Well, since the reciprocal of the function will never be allowed to have the value, to take a value of 0 for x, then all the points where x equals 0, when you think about it, are, well, obviously here at the origin, 0, 0, but this one has x coordinate 0, so everywhere on the y-axis, the x coordinate is equal to 0. So what that tells us is that all these points together will make a vertical asymptote. We just use a broken line for vertical asymptote. That's what we normally do for aesthetics purposes. But you can also draw the vertical asymptote using a solid line as well. Okay, now next we are going to continue with the rest of the graph here. But before we move on, I want to emphasize something very important. Whenever you identify the asymptotes, you have to label them by their equation. And in this case, we're going to say that the vertical asymptote will have the equation at x equals 0. Now, we have to find out the rest of the graph, what's happening here. And for this, we have to look a little bit closer in the graph of the function f of x. So at this point right here, the value of y is 1/2. So when you reciprocate 1/2, so 1 divided by 1/2, is the same as multiplying by the reciprocal, so that would be equal to 2. So we're going to say that at x equals 1/2, y equals 1/2 for the function, the reciprocal will be x 1/2, y will be equal to 2. Next, I will jump to this point in here where the y value is 1/4. So x is 1/4, y is 1/4. So when you reciprocate 1/4, 1 divided by 1/4, then we'll get 1 times 4/1, which is basically 4. So when x equals 1/4, the value of y will be positive 4. And as you can see here, the closer we get to x equals 0, so when x becomes almost 0, but not exactly 0, a little bit more than that, let's say, for example, 0.0001, then the value of y will be equal to, so remember that in the function y equals x and y are the same. And we need to mention this first. So the reciprocal of it is going to be quite a large number. 1 divided by 0001 will be equal to 10,000. So that tells us that the closer we get to x equals 0, the larger the y values become. So that means that the behavior of the function will be like this. So the graph will get closer to the vertical asymptote, but it will never cross the asymptote. So in the second lesson, this is the first lesson of Unit 2, but in the second lesson, I will explain this in much deeper detail, so how the asymptotes are formed. Now, in the same way, we reason about the next part of the graph. So remember that the vertical asymptote will always separate or divide the graph into sections. And this is only one of the sections, but there is still graph going and life going here on the left side of the asymptote. And the reasoning is the same. Now, what we are going, and another thing I want to mention here, so we make it shorter to analyze this section of the graph, is that when you look at this section of the given function, f of x, that's an increasing function. And when you look at the reciprocal, you see that the reciprocal is a decreasing function. So, or this portion of the graph is decreasing. And that is because any reciprocated increasing quantity, so when you reciprocate any increasing quantity, then we will get a decreasing quantity. So that makes sense, okay? Now, when you look at this graph in here, you see that the graph is also increasing, right? So remember, we read the graph left to right if we want to see if it's increasing or not. And when y value is -1, the reciprocal will be also -1. And this is a very important point that we always want to mark and make sure we show on the graph. And when x equals -2, y is -2. So the reciprocal of y equals -2 will be -half. The same way with when x equals -4, y is -4. Reciprocal of -4 will be equal to -1/4. So as you can see, the graph here will be approaching the x-axis. And as the y values become more and more negative, that for the function f of x we're talking about, then the reciprocal is going to get very, very close to 0, but it will never become 0. So that's why the graph, we say the graph is approaching the x-axis here. Now for this section of the graph, again, the same idea. At this point, the y value is -1/2. That means the reciprocal of it is going to be -2. And same when at y value here, at x equals -1/4, the y value is -1/4. You reciprocate -1/4, for this same x value, we're going to get the y of -4. And here we go again. So this would be the graph of y equals 1/x. I'm pretty sure you are familiar with it. I just wanted to go over it one more time together just to make sure that we remember the basics. Now, one last thing before we move away from this task is discussing the behavior of the function, the end behavior of the function. As you can see here, when the function here, the x values are approaching infinity, the function in here, the reciprocal function, is getting close to 0, never touching 0. And the same thing happens as x approaches -infinity. In a case like this, we're going to say that the y values of this function will never become 0. Or in other words, we'll say that the function will have an asymptote, because all these points where y equals 0, since y never becomes 0, right? So all these points where y equals 0, which is so many, it's the entire x-axis that will make an asymptote for the function. And since it is a horizontal line, we call this a horizontal asymptote. And of course, we have to label it by its equation. Now, we're going to take a look at the features of each graph. So for this, we're looking at the function given and the reciprocal and see how the features of the function are related to the features of the reciprocal. So the function f of x equals x will have the x-intercept at 0 and the y-intercept at 0. The vertical asymptote will be at x equals 0. We're talking about the reciprocal function. So the vertical asymptote is at x equals 0, and the horizontal asymptote is also at y equals 0. Now, for the given function, for the blue graph, as x approaches infinity, y approaches infinity. And as x approaches -infinity, y is approaching -infinity as well. Now, for our graph, as x approaches infinity, the y values will approach 0. And here is something that I want to mention. I don't know if you have been introduced to this idea before, but when we have numbers that are slightly more than 0 but almost 0, what we do is we put a plus in the exponent spot. It doesn't play the role of an exponent, but it just indicates that this number can be as close to 0 as we want it. Like it can be this big a decimal in a way. So in the same way, we're going to reason about the end behavior. As x approaches -infinity, this function is approaching 0, but in this case, this is a little bit less than 0, it's below the x-axis. So in this case, guess what? We're going to call this 0 minus, so slightly less than 0. Now, other behaviors that are of interest and we discuss often are behavior at the vertical asymptote. Now, the vertical asymptote is at x equals 0. So we want to approach x equals 0 from the right-hand side. So let me just point at it. So x is approaching 0 from the right-hand side, and we'll approach 0 from the left-hand side as well. So when x approaches 0 from the right-hand side, you see that the y values are getting bigger and bigger. So we'll say that the y values are approaching infinity. When x is approaching 0 from the left side of it, you see as we get closer and closer to 0, then the y values will approach negative infinity. Now, in what intervals is the function increasing or decreasing? So when we talk about increasing or decreasing intervals of the function, we look at the graph as if we are walking on it left to right, or as if you're reading a book. So I walk on the f of x equals x. I see my pen is going up all the time, so therefore this is increasing throughout its domain. Now, if it is increasing throughout its domain, it is never decreasing. Whereas the reciprocal function, right here, we're going to say that when I walk on this graph, my pen is going down, my pen is going down in here. So this is also decreasing throughout its domain. But be very careful to state the domain correctly. So the domain will be from negative infinity to 0, joined by 0 to infinity. We have to leave 0 out. And why is that? Because 0 is a vertical asymptote. So is it increasing? Well, never. And that is because it's decreasing throughout its domain. Now, in the next example, we have something similar. We made the equation of the linear function a little bit fancier, and here we go. You have the graph already drawn, and we are going to draw the reciprocal of it. Now, we can choose to follow the same idea by looking at each and every point, or we can use whatever we learned in here and practice in the next function. So we're going to say that wherever the graph of the function, linear function, had the x-intercept, a vertical asymptote happened. Here's the x-intercept of the given linear function. That means that right there, the reciprocal will have a vertical asymptote right here. So we're going to label the vertical asymptote by its equation, and we're going to name it vertical asymptote. And it seems that vertical asymptote is at x equals 2. And another way that you can actually treat this is by simply making this denominator 0 and finding where the 0 of it is. But we have the graph drawn for us. Now, next, what do we do? Well, next we will have to determine what is happening on the left side of the asymptote and on the right side of the asymptote, because our domain now is divided. It's not the set of all real numbers. We have an interruption in here, which means that part of the graph is going to be on the left side and part of it will be on the right side. So when you look at this graph in here, you see that this graph is decreasing. Guess what's going to happen to the reciprocal? So the reciprocal of a decreasing quantity is always equal to an increasing quantity. Now, our next question, though, is that it is increasing. I get this, but how is it increasing? Is it going like this? Is it going like this? So where is it going exactly? How is it behaving precisely? Well, one of the key points that we use is where y equals 1. The reciprocal of 1 will be equal to 1. The next point that I'm going to use here is the y value of 2. When y value is of 2, reciprocal will be 1/2. And as you can see in here, all these y values that are so large, when you reciprocate them, they will get very close to 0, never touch 0. So this will be the graph here. Now, the y value here is 1/2. It will become 2 when you reciprocate it. And as we get closer and closer to this asymptote, then the function is going to hit infinity. Now, In a similar way, we're going to say that here, where y is -1, the reciprocal will be also -1. Y is -2, the reciprocal will be -half. And as you can see, as the y values become bigger negatives, right? So they're going down, then the reciprocals will become or will get very close to 0, but still negative in sign. And in the same way, we'll have this graph in here as well. So this will be the reciprocal of -x plus 2. And as you can see here, we also have a horizontal asymptote right at y equals 0. So the vertical asymptote is kind of the same as, is found in the same way as before by stating the restrictions or finding the zeros of the denominator, we'll say. But the horizontal asymptote actually didn't change. It was y equals 0 at both cases. So we'll have to think about it. Now, let's talk about the intercept. So we have the x-intercept at 2. Vertical asymptote will be at x equals 2. The y-intercept in this case is equal to +2. That is just a coincidence. And the horizontal asymptote is at y equals 0. The end behaviors of the function as x approaches infinity. So we're going to say that when x approaches positive infinity, this function is going down to -infinity. And as x approaches negative infinity, the function is going up to infinity. Now, in a similar way, then we're going to discuss the behavior for the green graph, the reciprocal. When x approaches infinity, you see the y values are just below the horizontal asymptote, 0 plus, 0 minus. When x is approaching negative infinity, the values of y are just above the x-axis, so 0 plus. When x is approaching the vertical asymptote of 2 from the right-hand side, this is x approaching 2 from the right-hand side, 2 plus, and this is x approaching 2 from the left-hand side. So we're going to say that on the right-hand side, as the graph gets closer to 2, look at this, the graph is going all the way down to -infinity. So we'll write -infinity here. And as x approaches 2 from the left-hand side, the y values are approaching +infinity. Now, let's look at the intervals of increase and decrease. This function is decreasing for any real value, the given function. That means that is never increasing. Now, the reciprocal seems to be increasing, so we're going to say it's increasing for all values of x that belong to -infinity, 2, joined by 2 to infinity. So, and it is never decreasing. So this is a reciprocal of a linear function. Very straightforward. Review from grade 11. And again, thank you for learning with me. Please stay tuned because I will continue in the next video with the reciprocals of quadratics, where things start getting a little bit more exciting and more interesting. Bye for now.